Hello students, welcome back to this new session. Here I am continuing the same module, that is calculus of complex functions. Okay, here we will be seeing what is an analytic function and we will study the further details about it. What is an analytic function? Any function which is differentiable at any point given in the region. Okay, suppose you are having a function f of z defined in the region R and you are having a point z is equal to z0 in the region R. I'll just show you. Suppose this is the region R and there is a point z0 here. Okay, you are defining, there is a xy plane for you. Okay, there is an xy plane for you, the real axis and the imaginary axis with the origin. Okay, so you are having a point z is equal to z0. You are defining a function f of z for all of these points in the region R, and suppose there is a point z is equal to z0 at in this region R, and if your function f of z is differentiable at the point z is equal to z0, then f of z is said to be analytic at z is equal to z0. Okay, and also if the function is differentiable at each and every point present in the region R, okay, at all the points present in the region R, then the function is said to be analytic in the entire region R. Okay, w is equal to f of z. Okay, if I take this to be w, okay, w is equal to f of z will be analytic. Maybe if it is differentiable at each and every point, then we say that the function is analytic in the region R. Okay, in the complete region R. Okay, so there are other names for analytic function. It is also called holomorphic function or regular function as well. So it is also known as holomorphic function and also regular function. So they are all other names for analytic function. Okay, so any function which is differentiable at a given point, it is said to be analytic. Okay, so just remember this one important point. Okay, so now let us see the condition for any function to be analytic at a given. Now let us continue with the necessary and sufficient condition for any function f of z to be analytic. Okay, so here we will be deriving the necessary and sufficient conditions for any function to be analytic, and this is one of the important topics of your module 1. It has appeared so many times in the question paper. It is better if you take it as important. Let us derive this. Okay, what it says, first of all, let's see. Given any function f of z is equal to u of xy plus I into v of xy is said to be analytic if the partial derivatives dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y, they must exist and they must be continuous in the region R where the function f of z is defined, and they must satisfy the equations dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. These equations, they are called Cauchy-Riemann equations or CR equations. That is, in short I should say, we are deriving CR equations, that is the necessary and sufficient condition for the function to be analytic. Okay, so we'll be only proving the sufficient condition over here. Okay, let us work with the proof. So let w is equal to f of z is equal to u of xy plus I into v of xy be analytic. I'll just consider, let it be analytic in the region R. Okay, in the region R. If it is analytic, it means, when do you say it is analytic? If it is differentiable. Okay, it means f dash of z exists at all points in R, is it not? Because it is analytic in the region R, f dash of z must exist at all points in the region R. So what is f dash of z for us? F dash of z, by definition, we know it is limit as delta z tending to 0, f of z plus delta z minus f of z divided by delta z. This is by the definition itself, right? Now, I have told you in the beginning also, if f of z is equal to u plus iv, or you take u of xy plus I into v of xy, I can take f of z plus delta z. How can I write f of z plus delta z? It will be u of x plus delta x, comma y plus delta y, plus I into v of x plus delta x, comma y plus delta y. I hope it is seen there. Yes. See, if f of z is equal to this, so everywhere that delta z, to all the variables, that delta should be extra increment given to the variable z. It can be in any form. It can be delta x or delta y in both the values. Okay, so better you write a delta. Wherever you have x and y, you are simply adding delta, nothing else. So it's very easy step. So I'm going to just substitute the values of f of z plus delta z and f of z in this equation. I'm going to call this as equation 1. So f dash of z will be limit as delta z tending to 0. It will be u of x plus delta x, comma y plus delta y, plus I into v of x plus delta x, comma y plus delta y, plus minus u of xy minus I into v of xy. I hope it is clear there. Okay, that divided by, now delta z, in my previous session only I have told you it will be delta x plus I delta y. I'm going to write that same thing. So it will be delta x plus I delta y. Okay, or in short, if I write delta z also, it will be not an issue, because I am considering delta z tending to 0. Later we can see what is happening. We will substitute. We will keep it as delta z only over here. Okay, I hope up till here everything is followed to all of you. Now f dash of z will be limit as delta z tending to 0. Yes, now let us collect all the real and imaginary parts aside. So here we are having u of x plus delta x, y plus delta y, and here u of xy to be the real part. So let us collect the real and imaginary part aside and write them properly. This is the real part. The imaginary part I am collecting. I hope this point is clear to you. So this is going to be my equation 2, I will say. Okay, so this is my f dash of z. Okay, so this is my equation 2. In this equation 2, what will I do is, my delta z is delta x plus I delta y. Okay, let this tend to 0, because this delta z is tending to 0, means delta x plus I delta y tend to 0. Okay, it means I will consider delta z be wholly real. Wholly real means what? No imaginary part, is it not? No imaginary part means delta y tending to 0, delta is equal to 0, means delta z is equal to delta x. Wholly real means delta z is equal to delta x. It means delta y is 0. What you all say? The same thing I'll substitute it here. So my f dash of z will take the form limit as delta z tending to 0. This time, since delta z is equal to delta x, this will be delta x. I hope it is clear to you. Okay, so now u of x plus delta x, comma y plus delta y is 0, so we need not write it. Delta z is equal to delta x, write it. This is the real part. Here you have delta x, I into this, all we have as it is. Like how delta y was 0 here, same is here. So now I'll separate it. Okay, so to the limit as delta x tending to 0, this is 1 plus I into v of this whole thing divided by delta. I have just separated the terms, nothing else. Now tell me, what is this? This is separate, please make a note. Okay, so what is this? Limit as delta x tending to 0, u of x plus delta x comma y. There is no change in y, only x is changing. So is it not a partial derivative of u with respect to x? Is it not? So we can replace this complete thing by dou u by dou x plus I as it is. This complete thing is dou v by dou x. This is I. So let us call this as equation 3. Okay, we have got f dash of z to be, yes, if we are going along x-axis, considering y0, along x-axis f dash of z is taking this value. Okay, so hence we have got one part, half part of this derivation. Now we'll go for another part. Okay, how do we go for another part? That is, we consider delta z to be wholly imaginary. Okay, here only we'll do the changes and we'll get the result. 1 minute. Now let delta z be wholly imaginary. Then delta z will be equal to I delta y. Since delta x is 0, we are considering it to be wholly imaginary. So delta x is 0, so we are having this. So let us substitute those things over there in our equation 1 or equation 2 right now, not equation 1. So let us do that in equation 2. So f dash of z is limit as delta z tending to 0. U of x plus, since delta x is 0, need not write that, y plus delta y minus u of xy plus I into, this is the real part, the imaginary part we had in equation 2 as like this. Because delta x is 0, so I am not writing it, make it a note, and please maintain all of you the notes. It's very important to have a note of all my lectures. So since delta z is I delta y, and also here limit as delta z tending to 0, I did not write, because delta z is I delta y, I is anyway constant. When delta z is tending to 0, it means delta y must tend to 0 for that. So you have to change it like this. You need not take I delta y tending to 0 because I is constant. But in place of delta z, you have to write I delta y. Here we are saying delta z is tending to 0. That's why you have to take delta y tending to 0, because I cannot tend to 0. I is constant. Okay, so make a note there. Now limit as delta y tending to 0. Now again separate that. So 1 by I as it is. Okay, it's u of x comma y plus delta y minus u of xy over delta y, and plus I is getting cancelled. You just see that. V of x comma y plus delta y minus v of xy over delta y, because anyway I is got cancelled. Okay, now if you just have a look on this, you will see that this is nothing but 1 by I is anyway constant, get it outside. When you take this limit inside that bracket, you have, it is dou u by dou I, and this one is dou v by dou I. Now for this, if I complete equation, if I divide and multiply by I, it will be, yes, what is 1 by I for you? Rationalize this. You divide and multiply by I to it. Okay, it is I divided by I square. I square is minus 1. So I square, I divided by minus 1 or minus I you get. So 1 by I can be written as minus I. So minus I dou u by dou I plus v dou v by dou I. This is equation 4 for you. Okay, so this is very simple and very easy. It appears most of the time in the question paper, so all of you mark it as important. So we have done the next part. From equation 3 and 4, from equation 3 we have got this result. I'll write it again here. We have got f dash of z to be dou u by dou x plus I into dou v by dou x. Now compare the real and imaginary parts from equation 3 and equation 4. Compare the real and imaginary parts from equation 3 and equation 4. Anyway, both are the derivatives of f of z. Okay, they must be same. So compare the real and imaginary parts of the equations 3 and 4. You will have the real part in equation 3 is dou u by dou x. The real part in equation 4 is dou v by dou I. So dou u by dou x must be equal to dou v by dou I. And what is the imaginary part in equation 3? It is dou v by dou x. What is the imaginary part in equation 4? It is equal to minus dou u by dou I. So this is what the CR equations derived for any function to be, or the condition for any function to be analytic in that region. Okay, so this completes the derivation And hence, let us continue in my next session with the CR equations and some problems on analytic function. Then later we'll see on CR equations in polar form. Okay, continue in my next section. Thank you.